We're going to continue our study of rigid body kinetics, and in particular, we're going to look at special forms of the governing equations. So recall from Newton's second law, we have the sum of the forces is equal to the mass times the acceleration, and for a rigid body, more specifically, the sum of the forces is equal to the mass times the acceleration of the center of mass g of the rigid body. We can split this up into its components, x and y, and we have two scalar equations, one for x, one for y, where we look at the center, x component of the center of mass acceleration and the y component of the acceleration of the center of mass. Also, we've established in the previous video that the sum of the moments about the center of mass, g, is equal to ig alpha, where ig is the mass moment of inertia about the center of mass, and alpha is the angular acceleration. And so hopefully we were able to drive home the point that there is a certain analogy here between Newton's second law and our rotational equation of motion. Right, so we see that the sum of the forces induces a linear acceleration ag, and the sum of the moments, or the net moment, induces an angular acceleration alpha. And that resistance to changes in its state of motion, whether that is linear acceleration or rotational acceleration, it's either the mass or the mass moment of inertia, respectively. Okay, so now let's talk about free body and kinetic diagrams. So we all know what a free body diagram is. So on the left-hand side here, the left diagram is a free body diagram, which shows all of the external forces and even external moments, M1 and let's call this M2 here, on the rigid body. A kinetic diagram depicts what is the, essentially it is the right-hand side of the equations of motion. So we know that the sum of the forces is equal to the mass times the acceleration. So on the right-hand side, on the kinetic diagram, we're going to show the mass times the acceleration. So here we have the mass times the acceleration in the y direction and the mass times the acceleration in the x direction. For rigid bodies, we have one additional equation of motion, which is the rotational equation of motion. The net moment is equal to ig alpha. So the right-hand side is ig alpha, which we show over here on the kinetic diagram. So, on the left-hand side of the equation, the sum of the forces, the sum of the moments, this is what we show on the free body diagram. On the right-hand side of the equations, we depict those quantities on the kinetic diagram. And these two diagrams are equivalent. So one could think of this as one is causing the other, right? So a net force induces a linear acceleration, and a net moment induces an angular acceleration, obviously multiplied by a mass or a mass moment of inertia. So we show these quantities on the kinetic diagram. Now, what if we want to take the moments about point P? So in the previous video, we started doing this, but then we've idealized the situation and said, well, what if P is equal to the center of mass? And this greatly simplified our equations. So let's go back to an intermediate equation that we had in our derivation, which stated that the sum of the moments about an axis passing through point P is equal to the negative of y bar m apx plus x bar m apy plus I p alpha. So if this is looking foreign to you, I would encourage you to go back to the previous video and just find this equation here. So it would be advantageous to actually be able to express the above net moment on the rigid body in terms of kinetic variables at the center of mass. So these are these ones here that we're talking about. So first, let's recall the parallel axis theorem. which states that the mass moment of inertia about an arbitrary point P is equal to the mass moment of inertia about the center of mass plus the mass multiplied by the distance between the 2 points squared. We can also express this as Ig plus m x bar squared plus y bar squared. And this is useful because in many situations, IP might not be tabulated, but Ig will be. So if you look up tables for mass moments of inertias of typical shapes, you'll often find, or almost always find, the mass moment of inertia about the center of mass G. So it is useful to express IP in terms of Ig. So we're going to substitute this into the first equation and rearrange certain terms. And what this will give us is the sum of the moments about point P is equal to y bar multiplied by the mass multiplied by the negative of the x component of acceleration plus y bar alpha plus x bar m multiplied by the y component of acceleration at point P plus x bar alpha plus Ig alpha. So we're getting a bit closer to our goal where we can express the sum of the moments about a point other than the center of mass, but in terms of certain quantities at the center of mass, such as Ig, the mass moment of inertia. Now let's look at these quantities over here, the accelerations at point P. We can express this as, well, we can express Ag, the acceleration at the center of mass, as the acceleration at point P plus the relative acceleration and we can expand this into its components. And notice here that we're using x bar and y bar because this is essentially the distance between the point P and the center of mass G. So if we carry out the cross product and equate the I and j components, we're going to have AGX is equal to APX minus y bar alpha minus x bar omega squared. And in the y direction, we're going to have AGY is equal to APY plus x bar alpha minus y bar omega squared. So notice up here, we have these two brackets, which we can replace with terms from this equation here. So making these substitutions, so we will be replacing the quantities at point P with quantities at point G, we get this final form of the sum of the moments about point P is equal to the negative of y bar m multiplied by agx plus x bar m multiplied by agy plus ig alpha. And this is what we are after. So what is this saying? So originally, we developed this equation of motion over here, which states that the sum of the moments about point G is equal to the mass moment of inertia about point G multiplied by alpha. Now we may want to take the moments about a point other than G. So note that point P is not equal to point G. And what this equation here is stating is that the sum of the moments about point P is equal to what we call the sum of the kinetic moments. So let's look at our kinetic diagram. We have the mass times the acceleration over here, which has units of force, and we're multiplying it by a distance y. And this distance y is actually y bar and x bar. So we're taking the moment of this kinetic term over here about point P. So we have magx multiplied by y bar and magy multiplied by x bar. So this is what we call, over here on the right-hand side, the kinetic moments. So these are the moments due to the kinetic terms at the center of mass, but about axes passing through a point P, which is other than point G. So in shorthand, we can write that the sum of the moments about point P is equal to the sum of the kinetic moments, and again, about point P. And this is very useful, as we're going to see in the next few minutes. What we're going to do is that we're going to look at special cases of the equations of motion. The first one we're going to look at is just translation. So when the rigid body undergoes translation, all its particles have the same acceleration. So this suggests that alpha is equal to 0. The rotational equation of motion reduces to the simplified form of just the sum of the moments about point G is equal to 0. And as we have seen before, the sum of the forces in the x direction will be equal to the mass times the acceleration in the x direction, and the sum of the forces in the y direction will be equal to the mass times the acceleration in the y direction. So if you wanted to draw free body and kinetic diagrams, we could do that. And on the left-hand side is our free body diagram. We would have a bunch of forces here. So if we call this F1, F2, F3, F4, we may have some moments, M1, M2, and we have a center of mass G here with a body force of the weight. And this is equal to our kinetic diagram, where again our kinetic diagram shows essentially the right-hand side of our equations of motion. So we look at the center of mass and what is induced by those net moments and net forces. And so what we have is just a mass times an acceleration at point G. So what about fixed axis rotation? Let's have a look at this special case here. Fixed axis rotation. So let's consider a random body, and it is connected at this point here to, let's call this a pin joint or something like that. Okay. And we'll call this point O. Right, so this is the point about which the entire body is rotating. And again, we could have a bunch of forces here, F1, F2, F3, and some moments as well, M1, M2. And so we might have an induced angular acceleration, angular velocity, omega. And we have a center of mass over here, center of mass g. This is not quite a free body diagram, so let's turn this into a free body and kinetic diagram. So what we have, I'm going to try to draw this again here, side by side. So the free body diagram on the left, so again we'll show our external forces, F2, F3, F4. We might also have a reaction force at the axis of rotation. We can call this R if we want. So we have point O over here. We have the center of mass G, and we're also going to have a body force of the weight. Let's also draw some moments. Okay, so that's a free body diagram. So recall our kinetic diagram. We look at the center of mass, G, and we see what is induced by the equations of motion, or by the left-hand side of the equations of motion. So for fixed axis rotation, instead of using x and y components, it's more useful to use n and t components, where n is the normal component and t is the tangential component. So what we will have a mass times an acceleration in the normal direction, and a mass times an acceleration in the tangential direction. We're going to call this distance here between the center of mass and the axis of rotation. We'll call this RG. And again, the sum of the moments will also result in IG alpha. And so this is our kinetic diagram. So expressed in terms of the mass, the center of mass, so about the center of mass, G. Again, we have the sum of the forces is equal to the mass times the acceleration at the center of mass. But now we're just in a different coordinate system. Instead of x and y, we're in n and t, so we can write sum of the forces in n is equal to mass times the acceleration of the center of mass in n. And the sum of the forces in t, the tangential direction, is equal to the mass times the acceleration of the center of mass in the t direction. And we also have the sum of the moments about point G is equal to IG alpha. Now here, luckily, we actually know what form the tangential and the normal components of acceleration look like. So recall that the normal acceleration is equal to omega squared multiplied by r. And so in this case, r is, we call this rg, the distance between the center of mass and the axis of rotation. The tangential component of acceleration is equal to alpha r, or alpha rg in this case. So these are our equations of motion for fixed axis rotation, and these are the equations of motion expressed in terms of the center of mass quantities. Now it's often convenient to take the moments not about point G, but about point O. So perhaps, for example, we might not know what the reaction force is, but we can eliminate that by taking the moments about point O. So if we do that, let's write this out. So about point O. What does this give us? So let's assume positive is counterclockwise. So what we're going to say is that the sum of the moments about point O is equal to the sum of the kinetic moments about point O. So remember, this was just the result that we found up here, which states that if we want to take the moments about a point other than the center of mass, all we need to do is refer to our kinetic diagram and take the kinetic moment of those variables located at the center of mass about point P. So the sum of the moments about point O will be equal to, so we look at this diagram over here. So we have a mass times an acceleration in the tangential direction multiplied by the moment arm, which will be rg. So we have rg multiplied by the mass times the acceleration in the tangential direction. Now note that the normal component is passing through point O, so it exerts no moment. So all we have left is the Ig alpha term, which we add to our equation here. All right. Now recall that we know the form of AGT. AGT, the tangential acceleration, is just alpha multiplied by rg. So we write this out, and then we're going to factor out the alpha. So we have Ig plus the mass times rg alpha, rg squared multiplied by alpha. Now note that the bracketed term over here is just the parallel axis theorem, which gives us the mass moment of inertia about point O. So what we can say is that the sum of the moments about point O is equal to the mass moment of inertia about point O multiplied by alpha. So what we can do is add this as an alternate equation for the rotational equation of motion. So we can say that we can use either or, whichever one is easier to use in a given case that we are looking at. Okay, so in this video, we looked at some special cases or special forms of the equations of motion for a rigid body. So we started with the sum of the forces is equal to the mass times the acceleration, and we introduced the concept of free body and kinetic diagrams. In the previous video, we looked at the rotational equation of motion about the center of mass. And here we ask, what would this look like if we take the moments about point P instead of point G, the center of mass? And what we found is that the net moment about a point other than the center of mass is equal to the kinetic moments about that point. And those kinetic moments are the kinetic quantities multiplied, so the kinetic quantities at the center of mass G multiplied by their respective moment arms, which are x bar and y bar, the respective distances between the center of mass and the point P. We further looked at the equations of motion for translation and fixed axis rotation. Notably, what we found is that we have some useful forms for fixed axis rotation, particularly because we know what form the tangential and the normal accelerations will look like. In addition, we saw that if we take the moments about the axis of rotation, we can express the rotational equation of motion in a very shorthand form as the sum of the moments about the axis of rotation O is equal to just the mass moment of inertia about point O multiplied by the angular acceleration alpha.